be a re-engagement lesson for Unit 6. And now when looking at reactions, your standard reaction might look like A plus B reacts to give A and B. And a single replacement reaction might look like A plus BC reacting to give AC plus B. So there, the B and the A are going to switch or replace in reaction. And in a double replacement reaction, A plus B plus CD in reaction will give you AD plus CB. So the A and the D switching and the C and the B switching. And just remember that in these reactions, the metal is going to come first. So A and C might be the metals, whereas B and D are going to be your nonmetals. And the next step before balancing equations would be understanding ionic bonds. And in ionic bonds, your metal is going to give away one or more electrons to the nonmetal. And whenever in ionic bonds, the only thing actually holding the elements together are going to be electrostatic forces, opposed to covalent bonds where both of the elements are going to actually share electrons, and that's what's going to hold them together. In ionic bonds, your metal is going to lose an electron, your electron being negatively charged, so your metal is going to become positively charged. So your atom is going to start out neutral, and you're taking away or subtracting the electron, or negative charge. So in equation that might look like 0 minus negative 1, or 0 plus 1, giving you positive 1 for your charge. And as for the nonmetal in that reaction, or in that bond, it's going to gain an electron and become negative. So the 0 charge, or neutral charge, minus 1, giving you a negative 1 charge. So if you were to be given potassium chloride, then you know from the periodic table, K being in group 1 and chlorine being in group 7, potassium has 1 electron to give, so it's going to lose that electron and have a charge of 1, plus 1. And chlorine, only being able to accept 1 valence electron, will gain that negative charge also of 1, or negative 1. In the case of sodium oxide, oxygen can gain 2 valence electrons because it's in period 6. So 8 or 6 out of 8, it can gain 2. And sodium, it is in group 1, so it only has 1 electron to give to the oxygen. So in this bond between sodium and oxygen, you're going to end up having 2 sodium atoms and 1 oxygen atom. And as for the charges on those, oxygen is going to gain 2 electrons, so it'll have 2, or a charge of negative 2, whereas both of your sodium atoms are only going to give 1 electron each, so they're going to have a charge of positive 1. Do you have any questions about that? Now we're going to move on to predicting and balancing reactions. In a simple single replacement reaction, you might be given zinc and hydrogen chloride. So when you're given this reaction, what will your products be? Does anyone know?
zinc chloride and hydrogen?
Yes, because your metal is going to replace with a non-metal, and that's going to leave the hydrogen by itself. And when balancing, so this is not balanced, you don't even know what is or how many they are, but when it's balanced, you're going to have 2 HCl and zinc and 2 chlorides and your diatomic hydrogen. In another reaction, you might have diatomic fluorine and sodium chloride. Does anyone else know what your products might be? Yes.
Sodium chloride and chlorine.
Yes. Because your metal, sodium, is going to replace in reaction and bond to the fluorine. Now here we have a double replacement reaction, and I've already shown you what the products are going to be. So now we're going to balance this. The first step you're going to want to do is list out all of your elements or molecules in the reaction. So we're going to start off with potassium, chloride, lead, and then NO3 on the left and the right. And you're just going to count how many of each there are. So looking at potassium, there's 1 potassium, there's 1 chlorine, there's 1 lead, and there's 2 NO3s indicated by the 2 subscript after the parentheses. And on the right side, you have 1 potassium, 1 NO3, 1 lead, but you have 2 chlorine atoms. So when we look at our lists of atoms here, they're not equal. Because there's 2 Cl's on this side, only 1 on this side, and there's 2 NOs on the left, and only 1 on the right. So we're going to have to switch around and add some coefficients somewhere. So just start off by looking at chlorine. We're going to need 2 chlorines on the left. So we can add a 2 to potassium chloride. And whenever we recount our molecules, we're going to end up with 2 potassiums, 2 chlorides, still only 1 lead, and still 2 NO3s. And then going back to the right side, obviously potassium there's only 1 here, but there's 2 there. And same thing with NO3, there's only 1 on the right, but we need 2. So the next thing we can do is add a 2 to the 2 coefficient to KNO3. And then we're going to recount the atoms. That'll give us 2 Ks, 2 NO3s, 1 Pb still, and 2 chlorines. So 2, 2, 1, 2, 2, 2, 1, 2. So once you have the same number of all of the atoms, then you know your equation's balanced. So what we're going to do now is have some practice balancing reactions. I've already given you the products and the reactants. So if you could just balance those, it'll take a couple minutes. Which one?
It was the first one.
The first one?
But I just got one. Well, I got two coefficients wrong.
I'll just go ahead and do number one. Number one was definitely the most difficult. Yeah, problems like these are tough because just from looking at it, you can see that like the 3 here and the 2 here, you're gonna have to increase this, but then you're gonna have to increase this one and this one because this becomes 4 and then 6. So there's a lot going on here. So start with 2, 3, and 1, and on the right we have 1, 2, and 1. So if we increase this, or if we put 2 as our coefficient here, and since we have less O's on the right than the left, we can increase our coefficient by 2 here. And that's going to give us 2, but then 2 and 4. So on the right, we're going to have to increase our O's and our C as well. So we put a 2 coefficient on the first molecule, then we'll end up with 4 Fe, end up with 6 O's, and still 1 C. So we can go ahead and just put a 2 coefficient on the C, and then we have 2 there. So now on the left we have more O's than on the right, and more F's, Fe's. So we have to change our coefficient on the Fe to, we'll try 4. Yes, 4 Fe's. We're going to have to increase our coefficient on the CO2 because we need 6. So if we go 3 CO2, then that'll give us 3 C's, and 3 times 2 is 6 O's. 4, 6, 3. Now on the right, we have 1 less carbon. So if we change the coefficient on carbon to 3, then we'll be left with 4, 6, and 3. And then our equation is